Hi everyone and welcome back. So in this video what I'm going to do now is actually solve many problems using the concept of conservation of momentum. So what I did is I took the examples on the PowerPoint slides and I'm just going to solve them out for you. Okay, so I want this nearby actually. Put that over there. Okay. Turn this back on. Oops. Okay, so of course, as always, the context of this is a collision, so, the context is conservation of momentum, so obviously I'm applying this idea. So, anytime you have two objects combining, you should think conservation of momentum. So that's the approach you want to take to any sort of system like this. So here's our problem. We have a frictionless horizontal air table, so this has no friction. And we have a puck of that mass is moving toward puck B, which is initially at rest. After the collision, the puck A has a velocity to the left, and puck B has a velocity to the right. What type of collision is modeled? Which of the following quantities are conserved? What is the speed? And what is the change of kinetic energy? Okay, so I'm not going to answer these questions in order because actually I think in order to answer these questions you kind of have to start with this one, which is what is the speed. So before I do any sort of answering of any question, regardless of the question, I always draw a diagram because when you have a visual, it makes it a lot easier to apply the equation or write the equation that you need. So let's see, let's draw a picture of the situation. So we have puck A with that mass. So puck A has a mass of 0.252 kilograms and is moving toward puck B. So I'm moving toward puck B with that, which is initially at rest. So I'm going to assume that toward is forward, and this has is moving. So since there it is, puck A. So technically we don't know this, so I'm going to go ahead and just write down the variable like that to say that I don't know this. Okay. So puck B, with its mass of 0.370 kilograms, is actually initially at rest. So the initial velocity of B is 0. So that's my before. Now, it's incredibly important that you are organized when you do this, because really common things that people do is mix up the masses or velocities just because there's a bunch of them going on. So doing this drawing, which takes a little more time, gives you a little more visual and organization of how to solve this. So let's see. After the collision, puck A has a velocity to the left. So I'm going to go ahead and model that way. So puck A, with still a mass of 2.52 kilograms, now is moving to the left. So its final velocity is 0.116 meters per second. And puck B has a velocity to the right. Okay, so I'm going to draw it like this with B to the right. Still has the same mass, so it will keep its mass, and velocity B final then is 0.6545, I was writing it right, meters per second, like that. So there's our scenario. So first we really got to figure out this velocity. So let me just quickly go back to this. What type of collisions modeled above? I actually don't know. I can tell you what it's not. I can tell you it's not an inelastic just based on my drawing. So they're not sticking together. So it's some form of elastic collision, but I don't know which one until I figure out the change in kinetic energy, because that tells me my conditions. If the change in KE is 0, then that's my perfectly elastic collision. If KE is not 0, the change that is, then it's just going to be an elastic collision, or partially elastic. So notice that I can't answer this right now. And then same thing. I could definitely tell you that momentum's conserved. That is always true with our physics problems. There is no outside force because there's no friction. or any sort of thing that implies acceleration, so momentum is conserved. But I'll leave this blank because I don't know if energy is conserved yet. I don't. I literally don't. I solve it. So notice that if I find this, I can solve for this, which answers all of the questions. So questions are not linear, so just because they're in this order doesn't mean you have to solve them in that order. So you can always bounce around and see what you can do first. So even though I could write out the equation, I'm going to make my equation based on what I have. So I have mass A, the initial velocity of A, so that's the momentum, plus mv vbi should equal to mavaf plus mv vbf. So notice I wrote the equation based on what I see here. Now what I'm going to do is plug in my values. So I have 0.252 kilograms. I don't know the initial velocity, so I'll leave that as a variable. Then I have this value times 0. Now, in future examples, you'll notice that 0 times any number will be 0. So you can shortcut this by not even including it because technically it's 0, but I'm just going to leave it there because I want to show you how I'm applying the numbers. So that actually does go to 0. It's the same mass, so that will be the same number here, times VF. Oh, and hold on, let me, so remember velocity is directional, momentum is a vector, so we need to include this negative sign here to imply that this thing is going opposite its motion, which means to the left. So negative sign goes here. Now I modeled the direction with the arrow, which is why I didn't put it here, but you could put it there if that makes you feel a little better. It doesn't give you a double negative. This is saying it's negative because it's going that way. But that is necessary for these problems. Plus B, right? Now this is going forward, so we leave that as positive. Now notice, just to take a step back and to be really complete, notice that, well actually, it was moving toward it, and I assumed it was going forward. So we'll see if my assumption is correct, because I technically have it as positive here. How do I know if it's going to be correct? My final answer, if it's positive, it means I modeled the right direction. If the answer is negative, then I modeled the wrong direction, which means I just need to flip the sign. So we'll find out. Okay, so now this is calculation. So I'm going to go ahead and simplify this. So this is 0.252 kilograms times VAI, because this is 0. And as always, you can do this however you like. But I'm going to go ahead and do it in parts to make sure that I get it done correctly. .370 times 0.645. I'm just going to round to a few decimal places here. The units are kilograms meters per second because those are the direct multiplication of those two values. Okay, so I'm going to go ahead and simplify again. So I'm going to take those numbers. So take that number minus the 0.29, 209, roughly. I mean, if I officially round, it'll be 0.21, so fine, I'll officially round. And then this is still here. Okay, so this is all just algebra at this point. So VAI will be if I take this number and divide it over here. So 0.210 divided by 0.252. My final velocity is 0.833 meters per second. Now, the way I modeled it was forward, and this is positive, so it is forward. So this is to the right. I modeled it correctly. Random, just taking a step back here, if I did model this wrong, this would have came out like this, which is okay. It just means that it's going to the left instead, not right. So it's okay if you get a negative. If it matches, then you leave it, your diagram. If it doesn't match, you flip it. So I'm just going to go ahead and erase that for now. And leave it like that. Cool. So that's the first part. Very cool. Now the second part is we need to figure out what kind of collision this is. So we need to basically find out the change in kinetic energy. So you can do this in two different ways. I'll do it one way in this problem and another way in the other problem. It's the same method. You can do whichever one you like. So basically, I could do this. If the change of energy is 0, it's a perfectly elastic collision. If the change of energy is not 0, then it's going to be an elastic collision. So let's find the change of kinetic energy. So that means I need to find the total final energy and subtract it from the total initial energy. Okay, so this will be long, I'm sorry, but this is how we do it. So, the total final energy, so VFA squared plus the total final energy of B minus the total initial, sorry, that's nothing. Oops. Get rid of that little mark so I don't confuse people, sorry. Initial plus the total. So we have to include both conditions here. And then we're going to get an answer. So let's apply all these fun numbers. Okay, so I'm just going to go over here. 1/2. The initial A mass was 2.52. Okay, times the initial velocity of A, so that was the 0.833. I'm sorry, we don't want the initial, we want the final. I'm glad I kind of made a mistake there, because you can also make this mistake. So I need the final A, which is this number here. So negative 0.116 meters per second squared. Okay? Plus 1/2 B, I don't remember B, 0.37, yeah, 0.37. Times its final velocity, 0.645. And there it is, that's the first part. And then the second part, B1/2. So it's not too challenging, it is long. This is the 8.33 because that's the initial A velocity, that goes here. Times VIB, which was 0. Woohoo! I love when that happens, which means this whole thing will just be 0. Okay, also just a quick note about this. Since it's squared, it doesn't matter that the negative's there, but for completeness and the correct model of the question, you can leave that there. Alright, now it's just algebra, so I'm going to go ahead and do that. So 0.5 times 0.252 times 0.116 squared. Again, I do it in parts. 0.00170, because I'm going to round. And this is in joules, plus 0.5 times 0.37 times 0.645 squared. I get 0.078 if I round, minus, since this whole thing is 0, I'm just going to calculate that. 0.5, 0.252 times 0.833, 0.0874 joules. Okay, go ahead. 0.00170 plus 0.078. Okay, sorry. Which gives me 0.797. Now, since I combined these two, I'm going to subtract it from 0.0874. 4 is a terrible number, sorry. There you go, 4. Okay. Minus point, oops. Actually, I have it written. 0.08. So 0.0874. So what I get is negative 0.0077 like that joules. So, first of all, what does this mean? So let me just rewrite what we just solved for, right? We found the change in kinetic energy is equal to negative 0.0077 joules. So if we analyze this answer, notice that we lost energy, which makes sense. So that's what the negative means. Negative means we lost energy. We lost a small amount. I mean, this is about 0.1 when we look at it. So we did lose some energy. So I would say this is elastic because we lost some energy. Although honestly, I would almost consider this a perfectly elastic because it's such a small amount. So it's such a small amount lost here. So what's the original question? Let me just double check here. So frictionless. So actually, we only lost a small amount. So I would say actually, because it's frictionless, that we're mostly modeling a perfectly elastic here. So why? Even though it's a very small amount, super small, no friction, so there wouldn't be any energy loss. And these are pucks. These are, if you think about what pucks are, they're hard objects. So because of all of these conditions, I'm going to go with perfectly elastic, not elastic. I know elastic is usually because there is energy loss, but this is such a small energy that this is closer to perfectly elastic. And of course, to support my answer, it's a small amount, there's no friction, and these are hard objects. So the answer is perfectly elastic like that. So, we're done. Let's take a look here. We're going to go with, this is the better model. So I'm going to go with perfectly elastic. We got that. We got the change in energy, which was small. And I'm going to say generally that energy is conserved. Like that. Okay, so that concludes this type of question, which is one of the elastic energy questions.